Hi, I'm Maryam Atai, a PhD student in the sales program at WPI. I'm working on TCP slow start phase to improve its performance in wireless networks. So to optimize the internet connection, utilizing the full bandwidth and also avoiding packet loss is so important. So we introduce an approach that considers these two criteria to improve the performance of the network. So here you can see the nature of the TCP. In TCP, the sender sends data and receiver after receiving the data needs to acknowledge this. So for this purpose, it sends back ACK packet to the server. So server after receiving ACK packet doubles the congestion windows and send doubling data. This doubling happens in the first phase of the TCP and it's called a slow start. So here you can see the performance of the slow start and we can see that we have exponential growth until we have packet loss. After packet loss, it exits from a slow start and goes to the congestion avoidance phase. To avoid this packet loss, high start is designed to exit before packet loss and it works well on several networks, and so this is on default TCP. But we find that it doesn't work well on some high BDP networks like satellite. Here you can see an example that we download an object with different size when high start is on and when high start is off. And you can see that for each object, we need more time to download when high start is on in compared to high start off. So exiting from a slow start is so challenging. So we don't want to exit prematurely like high start because we have underutilization in the bandwidth. We don't want exit late like the default, like the traditional TCP, because we have overshooting and packet loss. And here is our goal. We want to reach the link capacity and exit before we have packet loss. For this purpose, we use the nature of TCP and we look at the send byte and deliver byte. As I said, we send data and we receive this, and by receiving the data, we double the congestion windows and send doubling data. So when we are under capacity, the deliver byte exactly follow the send byte. But after we reach the capacity, we can send more, but we cannot receive. Therefore, by comparing these two, we can find the capacity and exit from a slow start. But in this way, we have some challenges like the variable RTTs, and also as we only use the server-side information, we have the limitation in the memory. So we need to overcome these challenges. So for RTT, instead of considering the deliver byte for each RTT, we consider a window of deliver byte. That it means that the window covers several RTT, and so it smooths the variation. And so for the limitation in the memory, instead of considering each ACK packet, we consider a bin. That it means that we divided the window in several bins, aggregate the byte in each bin, and then aggregate all the window. And also, instead of considering deliver byte and send byte, we only track deliver byte, because as I said, when the receiver receives ACK packet, double the congestion windows and send new data. Therefore, by doubling the previous data, we can estimate the send data. For this purpose, here you can see the algorithm of our approach. When one window of the current deliver byte is completed, we need to shift back to can estimate how many byte is sent. So we shift back by current RTT and we find the previous deliver window. And as I said, we need to double this to estimate send byte. After we double this, we find the difference between estimated send byte and currently delivered byte, and we normalize this by dividing to estimated send byte. Then, for exiting from a slow start, we compare this normalized with the threshold that we have, and after that we can exit from a slow start. In our algorithm, we have some parameters like window size, threshold, and bin numbers that we need a default value for them. So for window size, we consider the average RTT during slow start and then do FFT on them, and then select the first peak of the FFT and find the periodic cycle, and then based on that we find window size. We do this on Geo, LEO, and 4G LTE networks, and based on these three we find the best window size is 3.5 of RTT. Then we have the threshold for exiting from slow start. Here we have the normalized difference versus RTT, and for different window size, and the green one shows our desired window size, 3.5 of RTT. And as I said, we need to exit after we reach the capacity and before packet loss. So when it graph goes up, it means that we reach the capacity, but we don't want to exit prematurely, and also we don't want to exit late. So we need a little time to this graph goes up. So here after 2 RTT with the 0.35 as a threshold, it's the best point for us. And also we have bin numbers. So we have bin numbers for one window, and also we need some extra bins for shifting back. And so based on our analysis, we find the bin numbers, the total bin numbers is 25. We evaluate our approach with Viasat testbed as Geo, Starlink testbed as LEO, and 4G LTE networks. And for doing this, we have several bulk downloads with iPerf3, and the download time is 45 seconds, and we have the sleep time about 60 minutes between each run. And we schedule to do tests during a day to cover all the times. And then set the parameters like the default that I set. And here you can see the result of one run over Geo, LEO, and 4G LTE. The left graph shows the estimated send byte and deliver byte. The blue one is the estimated send byte, and the green one is the deliver byte. And you can see that they are on each other. And after that, we have a difference between these two. So we can send more, but we cannot receive. So here you can see the difference between these two, the normalized difference. The vertical blue line shows at capacity point. The vertical red line shows the loss point. And our purpose is to exit between these two, after at capacity point and before loss. And you can see that with our approach, with the 0.35 threshold, we exit at the middle of the at capacity and loss point. And here we have for LEO and for 4G LTE. This table is a summary of our result for Geo, LEO, and 4G. And you can see that we have more than 96% timely exit, and as a conclusion, for high start on, as I said, it exit early, so we have underutilization. With high start off, the traditional TCP, it exit too late. We have overshooting and packet loss. And with our approach search, it exit accurately at the good point. And so we have some future work, like evaluate our approach on other wireless networks. We also want to add search in Quick in BBR. And as we can detect the exit point, we think about increasing the congestion window size growth.